Redox reaction. This is chapter 15. In redox reactions, the electrons are transferred from one reactant to the other, and it is the combination of reduction and oxidation. So the redox RED comes from reduction, OX comes from oxidation. So the combination is redox. The oxidation in redox reactions is the loss of electrons. The reduction is the gain of the electrons. Here you can keep in mind using this example. Leo says Leo loss of electron is oxidation and the gain of electron is reduction. This is one example. The magnesium metal burns in air, and so by burning, magnesium metal gives off electrons, 2 electrons. So here it is balanced because of the oxygen and next one. So because it has lost electrons, the process is oxidation. So we call this oxidation half reaction. The other half has to be reduction. And the oxygen molecules, they capture 4 electrons, and so that is reduction, half reaction. The other example is if you put a zinc bar in the aqueous solution of copper sulfate, the zinc will give off electrons. Zinc metal will give off 2 electrons, and the copper ions in the solution, they will capture those electrons and become metallic copper. So at the end of the reaction, you will see metallic copper, and the metallic zinc has been converted to solution, so it is ion part of the solution. Another example is if you have a copper bar or copper metal in a solution of silver nitrate, the copper will release 2 electrons, copper 2 ions, and silver ions will capture those electrons, become metallic silver. And this is another redox reaction, another example to redox reaction. So the original meaning of redox reaction, the oxidation, is reaction with oxygen. For example, in the burning of the substance and rusting of iron, the oxygen removes electrons from atoms, causing them to become oxidized. So here we got oxygen and we got iron. So under the water, under rain and so on, it becomes rust. So that is iron oxide basically. So it captures the oxygen, combines with the oxygen, and this is the reaction here. So iron, it has oxidation. So that the iron from 0, we will come to there, 0 to here it is plus 3. So that is the oxidation. It has captured oxygen. Reaction with oxygen. So that is oxidation process. And for the oxygen here, it goes from 0 to -2. We will then that is the reduction reaction here. Similar way, methane burns. This is methane gas. It reacts with oxygen and forms carbon dioxide and water. So you see here, carbon reacts with oxygen, becomes carbon dioxide. So that is oxidation. And oxygen, it captures hydrogen. So that is called reduction. Becomes reduced. The other meaning, there are several other meanings of the oxidation and reduction. One is the gain of oxygen, we just talked about, that is oxidation, and loss of oxygen is called reduction. The second meaning is loss of hydrogen, is oxidation, and gain of hydrogen is reduction. We saw that in the case of methane burning in oxygen. The third one is loss of electrons, and that is oxidation, and gain of electrons is reduction. And finally, increase in oxidation number is oxidation, and decrease in oxidation number is reduction. So if you see, for example, an element goes from 0 to +2, for example, that is an increase in oxidation number, so that's oxidation. If something goes from a negative, well, 0 to -1, for example, that's reduction. The oxidation number goes down. To solve to deal with the redox reactions, most of the time we have to balance those reactions. So the first thing we have to do is to assign the oxidation numbers. We have to know the oxidation numbers for each element in the reaction. So the oxidation numbers are similar in many respects to the charges on ions, but they are not the same. For example, the charge on the atom, the sign comes after the number. So it's like 2 plus, that is the charge, and aluminum is it has 3 plus charge. Chloride, for example, has -1, so we don't write 1, but negative means it is -1. The oxidation number, we show it as On, is written above and below each atom symbol, and the positive or negative, the plus or negative sign is written first, unlike the charge. So the oxidation number is written as +2, not 2 plus. So, and when we write those the oxidation numbers, we write on top of the element. So aluminum is +3, each chloride is -1, and so on and so forth. And there are several rules to assign the oxidation numbers, and assign each atom in an element an oxidation number of 0. If it is free element, for example, if sodium is by itself, carbon by itself, it is not part of a compound, or oxygen by itself, like sulfur or chlorine, then we assign zeros to those elements. We will see examples. To assign each atom in a monoatomic ion an oxidation number equal to the charge on the ion. For example, aluminum, if we have aluminum ions in the solution, because the charge on aluminum is 3 plus, then the oxidation number would be +3. So these are monoatomic ions. Sulfide, it has 2 negative charge, so the oxidation number will be -2, and so on. For particles, not elements, or monoatomic ions, we put above each hydrogen atom, we put 1. So in general, that means that in general the oxidation number for hydrogen is +1. There are some exceptions, but this is in general. You will see that in general chemistry 1. For oxygen, the oxidation number is -2. I mean, there are a few exceptions, but this is in general. So whenever you see an oxygen as a part of a compound, just assign -2 for that oxygen, and +1 for hydrogen. So if you have group 1 elements like lithium, sodium, potassium, and so on, assign +1 on top of that element. If you see group 2 elements like magnesium, calcium, and so on, assign +2 for that element. So these are the rules that we can keep in mind, and to find the other oxidation numbers. So for sodium hydroxide, for example, we have sodium because it belongs to the group 1, we put +1. And oxygen is -2. One of the rules was about oxygen, -2. And for hydrogen, whenever we see that, we assign +1 as oxidation number. 4, assign the remaining oxidation numbers so that the sum of all the oxidation numbers equals to the overall charge on the particle. We will see the example what we mean that. So you add up all the oxidation number. If the molecule is neutral, then you will have to equal the sum of the oxidation numbers, pluses and negatives. It has to be 0. If the ion, a polyatomic ion, has -2, for example, when you add up all the charges, it must be equal to -2. How we do that first, we need to write the symbol for the particle, the compound, or the polyatomic anion or monatomic, including its charge, if any. 2, we need to write the rule-defined oxidation numbers for each atom. Remember, oxygen is -2, hydrogen is +1, group 1 element is +1, and so on and so forth. Below each symbol, write the known oxidation number sum. That is, we multiply the oxidation number by the subscript here. 4, fill in numbers below each atom so that the sum of bottom numbers equal to the overall charge on the particle. So we will solve the problem, see these steps here, and then divide each sum by the atom subscript to get the oxidation number. For each individual atom, write that each individual oxidation number above each remaining atom symbol. So let's work on one example here. Fill in this diagram for well, there is no diagram here, but nitrogen dioxide here. So we can yeah, that is the so each one. So we got nitrogen, we got oxygen, we got 2 subscript here, and for each element, we know that according to the rule, we know the oxygen we put -2 on top. So that is the rule, but we don't have a rule about nitrogen. And in bottom here, we multiply this subscript by the oxidation number, so that is -2. So the total negative charge or negative oxidation number is -4. Because there is no charge on NO2, it is neutral, then you have to have a positive charge that when you add them up, you come up with 0, and that has to be a +4, right? +4, because when you add +4 and -4, that equals to 0. 0 means it is neutral because we don't have any charge on nitrogen dioxide. It is +2, +4. So that is what we see here. Okay, so let's work on a few more examples here. Here we got 3 compounds, and we know we want to find the oxidation numbers for each of those elements. In sodium iodate, we got 3 elements: sodium, we got sodium, iodine, and oxygen. And the rules, based on our previous rules that we talk about, sodium is +1, oxygen is -2, but the iodine we don't know. There is no rule about, but we can find it. So sodium, we just add up the oxidation numbers, +1. The question mark is for iodine. We don't know its oxidation number. And for oxygen, because we got 3 oxygens, we multiply by each of those oxygens oxidation number, which is -2. And because there is no charge on the molecule, it is neutral, we equal those numbers to 0. And so this will be -6, right? And -6, and this is +1, that will be -5, -5 all over, and then you will move this to the other side, and it will become +5. So your oxidation number for iodine will be +5. If you put +5 here and add the numbers up, you come up with 0. For iodine heptafluoride, we know here fluorine. We forgot about the fluorine is another rule. The fluorine is always has -1 charge. So whenever you see fluorine, just assign -1. But iodine, we don't know that. So iodine plus 7, because we got 7 fluorines, and multiply by its charge -1 equals to 0 because it is neutral. So it will be what? -7. So it has to be +7. So you just move this, the question, you leave the question mark alone and move this to the other side. Or you can add +7 both sides, and so those +7 and -7 will cancel out, and on the other side you will have +7. So the oxidation number for iodine is +7. So here we got 3 elements: potassium, chromium, and oxygen. Now we know the rules about potassium and oxygen, right? Potassium belongs to group 1 element, so it is +1. Oxygen is -2. So from there we can find the oxidation number for chromium. And so we put the numbers. We got 2 potassiums, so each one is +1. So 2 times +1 plus chromium, 2 times chromium, because we're looking for the oxidation number of individual element. So 2 times question mark plus we got 7 oxygens, so each one is -2. That will be -14. So you add them up, and you come up with +6. So here this will be -14, right? This will be +2. So -14 plus 2 is -12. So -12. So it will be 2 less 2 question mark equals to so you have to move the -12 to the other side, so it becomes +12, and you divide both sides by 2. So that question mark. So question mark stands for chromium. So chromium will be +6, the oxidation number. So this is another example here. Bicarbonate. You see here, unlike the previous 3 compounds, it has a charge here. So we know the oxidation number for oxygen and for hydrogen, so we can find for carbon and plug in the numbers. +1 is for hydrogen, carbon is question mark, we don't know yet. We got 3 oxygens, 3 times -2 equals to -1 here, you see. Is instead of 0 here, because those were neutral, but here this is polyatomic ion, so we have to equal it to -1. If it were -2, then it would have to be -2 equal to -2, and so on. So when you solve the problem, here you have -6, -6 plus 1, this 1, so that's negative yeah, negative, that will be -5, and so you just move the question mark. To leave the question mark, you have to move this -5 to the other side. So question mark equals to -1 plus 5, so it will be +4. So the oxidation number for carbon is +4 here. In redox reaction, the number of electrons lost by one reactant must equal to the number of electrons gained by another reactant. That is helpful to know when we balance the equations here. So every redox reaction is a result of two half reactions, one that loses electrons and the other that gains electrons. But those two numbers, I mean, the number of electrons that has been lost equal to the number of electrons that has been gained. For example, when lead metal is placed in a solution of silver ions, like silver nitrate, for example, lead atoms dissolve as silver metal forms. So now here you have lead, metallic lead, and it goes from because remember we said the pure elements, they have oxidation number of 0, and it goes from 0 to +2. That's oxidation. The oxidation number has increased, right? So that's oxidation. And silver here, it is +1. Now it becomes metallic with 0 oxidation number. So that is a reduction. So we can once we assign that, once we find it out, you know, which one is being oxidized, which one is reduced, we can just write those two half reactions. So in the first one, that's the oxidation. So metallic lead gives off 2 electrons, becomes lead +2, 2 plus. And the second one is because lead has given off 2 electrons, you have to have 2 silvers, because each silver captures 1, and you have to have 2 silvers to capture those 2 electrons that are released by metallic lead. So those are the half reactions. So in half reactions, electron can be reactants. Reactants, you know, the species, chemicals that appear on the left side of the arrow. So this is the arrow. These are reactants, and these are products. So we can treat the electrons as either reactant or product. In case of lead, the oxidation, the electrons are considered to be the product. In case of silver, the electrons are reactants. So that's how we can deal with half reactions. If we add the two half reactions, the 2 electrons on each equation cancel out. So for example, here you got 2 electrons on the right side of the arrow, and in the second reaction, the reduction reaction, half reaction, they will cancel out. And so when you add up the species on the left side of the arrow, we got lead and we got 2 silver ions. And then you have arrow, and on the right side you got lead 2 plus and silver, metallic silver. So that is your total, your overall redox reaction. To balance the half reactions, first we supply coefficient that balance the atoms. The second, we supply electrons to balance charges. Again, this is for half reactions. So example to this is bromine. It's been converted to bromide. So to balance the atoms, first we have to balance the atoms. You see we got 2 bromines on the left side, we got 1 bromine on the right side, and so you have to multiply the product bromide by 2. So you have to put 2 in front of this bromide. Now you got 2 bromines on both sides, regardless of the charge. Now, so if you multiply this, so 2 times -1, so that is the charge is -2. The charge is -2. So you have to add 2 electrons, because electrons are negatively charged, to the left side of the half reaction to balance the charge. Now you got 2 negative, -2, -2, so the charge is balanced. So we got 2 bromines, 2 bromines. So both the atoms and the charge are balanced. Balance. Okay, first balance the atoms again, to remember again. then balance the charge. So let's deal with the complete redox reaction. Again, in the previous example was the half reaction. So in this case here, we got magnesium reacting with hydrogen ion. It forms, magnesium has been oxidized to magnesium plus 2 plus, and hydrogen is 0. Remember, the free elements, they have oxidation numbers of 0. So here, because we got 2 here, the first thing we do is to balance the atoms, right? The magnesium are fine. We got 1 magnesium here, 1 magnesium. Those are balanced, but to balance it, we have to put 2 in front of hydrogen. So the atom-wise, they are balanced. We got 1 magnesium, 1 magnesium, 1 magnesium, 2 hydrogens, 2 hydrogens, right? Let's see if the charges are balanced. We got 2 plus 2 here, 2 times 1, that's plus 2, and here we got plus 2. So there are the charges are balanced as well. So both atoms and the charges are balanced. This is another example. Aluminum reacts with hydrogen, that is acid, that comes from acid, and the aluminum is being oxidized to plus 3, and hydrogen is being reduced from plus 1. So here it is plus 1. Here it is 0, right? So aluminum has been oxidized. And again, the first thing is to balance the atoms. Aluminum are balanced, 1, 1. Hydrogen is, we got 2 here, we got 1 here. So when you put 2 in front of hydrogen ion, that will balance the atom, hydrogen atom. Now we got 2 hydrogen atoms on both sides. So let's see the charge. Here we got 2 times plus, so that's plus 2, and here it is plus 3. Now, again, here we can't, you might think if we put 1 electron on the right side, then it will balance. That is only for the half reactions. For the complete reaction, we have to balance the charge by changing the coefficients. And here you see the only way to balance it is if we put 3, this 3 here, the absolute number, of course, in front of hydrogen, and put this and this in front of. So you see here 2 and 3. So if you put this so 2 in front of this, 2 in front of aluminum, and 3 in front of there, that will be 3. So you just multiply 3 by 2, that will be 6. And this 2, this 2 here, you put it in front of aluminum, that will be 2. And now if we multiply, if we find the charge here, that will be 6. For hydrogen, it is plus 6, and on the other side, we got 2 times plus 3. That's plus 6. You see, the charges are balanced as well, and while balancing the charge, the hydrogen number of hydrogen atoms and aluminum, they become unbalanced. So you have to put 3 in front of hydrogen here and 2 in front of aluminum to rebalance the atoms. Again, the first thing we do is to balance the atoms, and then we have to balance the charges. So charges, now here, as we did here, we just need to, kind of use the prefixes. I mean, the only way to balance the charges is using 2 and 3 here. So you have to have those charges balanced. And so while you balance the charges, if the number of atoms are the balance is gone, then you have to rebalance the atoms. That is what we did here, right? So once we have 6 hydrogens, you can put 3 to make it 6, the other side. And aluminum here, it is 2 now, so you have to put 2 in front of the product on the left side. Again, we know the oxidation is the loss of electrons and reduction is the gain of electrons, and then the oxidizing agent and the reducing agent. So we'll talk about the reducing and oxidizing agent here. Again, agent, like travel agent, it does what? It facilitates the travel, not necessarily has to travel, right? So here, when we say oxidizing agent, we're talking about the reactant that facilitates the oxidation process, okay? And the oxidizing agent is the one that accepts electrons, that gains electrons, so it facilitates the oxidation. The reducing agent is the reactant that facilitates the reduction process. So, and that is what loses electrons. So we will see more examples. So, and always, in a redox reaction, you must have one reactant must be an oxidation agent, and the other has to be a reducing agent. And again, the reducing agent is oxidized and it loses electrons. So remember, Leo, the line says Gerr, so losing electron is oxidation. So if something loses electron, it has been oxidized, and and that's why it reduces the other reactant. That's why we call the oxidized species reducing agent. So if something is reduced because it has gained electrons, and if something is reduced, it facilitates the oxidation process. So it is oxidizing agent. So let's work on a few examples here. Zinc reacts with copper sulfate. Now this physical state is solid, it's metal. AQ means it is in the solution, copper sulfate in solution. So you have copper ions, copper 2 ions, and sulfate ions. Here zinc sulfate becomes aqueous, so it does zinc, and here it is +2, and copper is 0. So let's see, because zinc is being oxidized, we know the sulfate is -2, the whole thing. The whole thing is -2, and this has to be +2, the oxidation number. And copper here is 0. Here zinc is by itself, free element is 0. This sulfate is -2. This is +2. So zinc goes from oxidation number 0 to oxidation number 2, and that happens by giving off 2 electrons. So zinc is oxidized. So because zinc is oxidized, it has to be a facilitator for the reduction of copper, because copper here, you see, it goes from +2 to 0, and by gaining those 2 electrons. So these 2 electrons are these 2 electrons. So zinc releases those 2 electrons, copper ions capture those 2 electrons, and so copper is what? The oxidation number goes from +2 to +2 to 0. So that is reduction. So because copper is reduced, it facilitates the oxidation of zinc, metallic zinc. So if we don't have copper, then zinc is not going to give off its electrons. It's not going to be oxidized. So copper 2, this copper 2 plus, has to be in the solution to facilitate the oxidation of zinc, metallic zinc. Similarly, the copper cannot gain those 2 electrons to get reduced unless we have zinc, metallic zinc in the solution, in the medium. So that's why the copper is reduced, copper 2 is reduced, but in the same time it facilitates the oxidation of metallic zinc. So they depend on each other. Without metallic zinc, copper cannot capture those two electrons and get oxidized. Without the copper 2 plus, zinc cannot be oxidized. So they depend on each other. They have to be in the solution together. All those two have reactions. A question here: copper wire reacts with silver nitrate. This is copper wire, is metallic copper, form silver metal. What is the oxidizing agent in the reaction? So the first thing to answer to answer this question is to write the chemical reaction. So we got copper wire is solid, metallic. Silver nitrate is aqueous, it's soluble in water, and then it forms copper nitrate and metallic zinc. So first of all, we know that the oxidation number of free elements is 0, so silver and copper are 0. And here we know nitrate is -1, so this is +1, silver is +1. So we got 2 negative here, so that's 2 times -1, -2. The nitrate is -2, so copper is +2. So we know here that copper has gone from 0 oxidation number to +2 oxidation number by giving off 2 electrons. So when the loss of electron is what? Is oxidation. So copper has been oxidized, and silver, on the other hand, captures 1 electron. Well, you have to have 2 electrons, of course, but this is just when we balance, because copper releases 2 electrons, you have to have 2 silver ions to capture both. But for the sake of discussion here, we just show the simplest form. So silver gains an electron. So gaining an electron is reduction. You can also tell from the oxidation number, it goes from +1 to 0. That's the reduction, right? Because silver is reduced, it facilitates the oxidation of copper, metallic copper. So the silver ion is the oxidation agent. So it facilitates the oxidation of copper. It is reduced, but it facilitates the oxidation of copper, so that's why we call it oxidizing agent. Another example here is the copper metal being oxidized or reduced. Again, to remember that the copper in free form, it is 0 oxidation number. So here it is +2 because this is monoatomic ion. Its charge is +2, so the oxidation number has to be +2. So the oxidation number is this 2 plus. The charge, that is the charge 2 plus. So the oxidation number we write on top of the element, in this case ion, copper ion. So what happens to the oxidation number here? It goes up, right? So when the oxidation number increases during the redox reaction, that is oxidized. So copper metal is oxidized. Okay. How about silver? We see that it goes from +1 to 0. That's free element, so that's reduction. So silver ion is reduced. We already answered that one, right? So you just look at the charge, and during the process it goes from ionic silver to metallic silver, so the oxidation number goes down. So is the silver ion acting as an oxidizing agent or a reducing agent? Another question about oxidized. So we know that silver is being reduced, right? Reduced. So while it is reduced, it facilitates the oxidation of copper from 0 to 2 plus, right? So a silver ion is acting as the oxidizing agent. Silver itself is reduced, but it facilitates, by reducing, it facilitates the oxidation of metallic copper from 0 to plus 2. So here, it's a complicated one, but let's assign oxidation numbers to all those species here. The question was, so this is permanganate reacts with chloride in water, manganese 4 oxide, and chlorate and hydroxide ions. So the first thing we do is we assign the elements that we already know the rules about, right? So we know that in manganese, this permanganate ion here, we know that oxygen is -2. We have a rule about oxygen. And in bottom here, we put the total, the sum. So we got 4 oxygens. 4 times -2 is -8. So here you got -8. But for manganese, we don't know that. The other thing here, just keep in mind that the permanganate has -1 here. That -1 belongs to 4 oxygens and 1 manganese atom. So it is polyatomic ion. So that means that when the sum of these oxidation numbers will have to equal to -1. So what number do you have to put here so that it is, when you add those two numbers, would give you -1? So that has to be +7. Okay, so because when you add those two numbers, you come up with this charge on the molecule. So and the charge, the oxidation number of manganese is 7. Chlorine here, that is monoatomic ion. So it has to -1, and here also it is -1, right? The other one is on the other side, this manganese 4 oxide. So the manganese here has plus. So we'll see that if it is +4. Now the oxygen, we know the oxygen is -2 because we got 2. We got 2 here, so you multiply it by -2, so you come up with -4. Now here it doesn't have charge; it's 0, right? It doesn't have charge, so that means when you add up the negative oxidation number and positive oxidation number, you have to come up with 0, and so that has to be +4. So in this case, on the right side, the oxidation number of manganese is +4. For chlorine here, we know the oxygen is -2, so we got 3 of those, that's -6. So it is not neutral, it has -1. So when you add up the negative oxidation numbers and positive oxidation numbers, it has to be equal to -1. So what number will give you, what positive number when it is added by -6 will give you -1, and that has to be plus 5. So oxidation number of chlorine in here is +4, and the other things are fine. So you see we have assigned all the oxidation numbers for this reaction here, redox reaction. Question 2 is write the formula for the reactant particle with an atom being oxidized. So out of those, which atom? So there are 2 changes here. Manganese goes from +7 to +4, so that is a reduction. Chlorine, it goes from -1 to +5. That's oxidation, right? So chloride is being oxidized, okay, in reactant side. So it's -1. So it is the chloride ion is being oxidized. So what is being reduced? Manganese in permanganate, right? We'll see. So in the same reaction, write the formula for the reactant particle, that is the oxidizing agent. So oxidizing agent means the one that is reduced, and the one that by reducing it will oxidize the other part. So here you see manganese in permanganate is being reduced from +7 to +4, so that's reduction. So manganese has been reduced. By reducing from +7 to +4, it facilitates the oxidation of chloride from -1 to +5. So the permanganate ion is the oxidizing agent. So in a balanced redox reaction, the number of electrons lost by the reducing agent must equal the number of gained by the oxidizing agent. So we know that. So let's, based on that knowledge, let's balance this chemical reaction here. And again, before we balance any equation, we have to assign the oxidation numbers. And this is how we assign those. We know sodium is in group 1, so it has to be +1. Chlorine, we have to find it. We know that oxygen is -2. So we just apply the same rules that we've learned so far. So because it is neutral, so this will be, oxygen will be -6, right? This is +1. So the chlorine has to be +5, because to add those numbers up, so just imagine this 5 is unknown. We put X mark there, and it has to be +5, so that when you add +5 +1, that's +6, -6, that's 0, neutral. Okay, and the other one is the hydrogen here. We know it is +1. And there is no rule about iodine, but because they have to balance each other, so it has to be -1. Iodine here, it is by itself. Its oxidation numbers is 0. Water is +1, -2. That is from the rule. And sodium is +1. Chlorine has to be -1, because they have to, when you add up those oxidation numbers, it has to equal to 0. So what we have here, we have assigned the oxidation numbers, and from there we can see how many electrons have been traded, have been given off or accepted. For chlorine, it goes from +5 to -1, so that is what? It's reduction. Reduction is gain, number of gained electrons. How many electrons are gained here? From +5 to 0, that is 5, to -1, that is another electron. That's 6, total of 6 electrons have been gained by chlorine in sodium chlorate. And for iodine, in here, it goes from -1 to 0, so that is only 1 electron lost. So now we know that how many electrons are gained, and right, so 6 electrons have been gained, 1 electron has been lost. And the next goal is to make sure we equal those number of electrons by some. So we have to find a lowest common multiple, so that we can balance those electrons, right? And for chlorine, we know is 6 electrons gained, and the other one is 1 electron lost, and the common number is 6. So you multiply this by 6, the other one by 1. So now if you multiply this HI by 6, that will balance the number of electrons. So let's rewrite the equation. So just ignore the oxidation numbers so we can clearly see the reaction. So here you see this 6 we put from this balanced here, and here we have 1 here, but we don't show ones. Whenever you don't see anything, it is a 1. So let's see if everything is balanced. We got 6 hydrogens here. We got 6 iodines, right? 1 iodine, there are 2, so we need to balance that. And hydrogens here, it has to be 6. So we need to, after that 6, we can go ahead and put 3 in front of iodine and 3 in front of water to balance the equation. So see, we got 6 hydrogens here, 6 hydrogens here. Okay, we got 6 times 1, 3 times 2 is 6, so 6 iodines, 6 iodines. Sodium is 1 here, 1 here, balanced. Chlorine is 1 here, 1 here, balanced. Let's see oxygen, how many oxygens we got. We got 3 oxygens here, 3 times 1, 3 oxygens here. So the redox reaction is now balanced. So let's balance another example. Potassium iodide reacts with oxygen, with water, and then it forms iodine gas. Iodine solid, it is solid, and potassium hydroxide. So again, the first thing we do is that this is redox reaction. How do we know that? Because you see, oxygen is by itself. Now it is part of the compound. It's not here. Okay, so you know that this is 0 and this is -2. Similarly iodide here, it is this is +1, this is -1, here it is 0. So when you see a pure element, most of, and it's been converted to part of compound, that is a redox reaction most of the time. So here, and the first thing we do is to assign the oxidation numbers. We know we have a rule about potassium is +1. It is group 1 element, and so iodide has to be -1 to balance the charge because it's neutral. Oxygen is a free element, is by itself, so it is 0 in water, +1, -2, so total this is +2, -2, so they balance at 0. Iodine is free element 0, potassium is +1, oxygen is -2, -2, and hydrogen is +1. So when you add those numbers, you come up with 0. And the iodine is here, iodide, it goes from -1 to 0. This is one electron, and the oxygen is 2 electrons gained. So what we do, we put 2 here, 1 here, we multiply by to just balance the number of lost and gained electrons. So here, 1 iodine gives 1 electron lost, and here oxygen 2 electrons from 0 to -2. So that will kind of balance. So that's why we have to put 2 in front of this potassium here. This 2 here. Here we multiply oxygen by 1, so they doesn't we don't show ones. Now you have 2 here. And that makes what? That makes this iodine balanced. Potassium is unbalanced, so you have to put 2 in front of this one to balance the potassium, right? So now potassium is balanced by putting this 2 because of this 2 here. So iodine, we got 2 here, 2 there. And what else? Oxygen. So here, oxygen, we got 2 oxygens here, 2 oxygens, and on the other side we got 1 oxygen here, 2 here, that's 3, right? So we can't play because now hydrogen is balanced, so we can't play with water. we can, if we put 1/2, if we multiply this by half, so here there are 2, the half is 1, 1 plus 1 is 2, right? So now we got 2 potassiums, 2 iodines balanced. We got 2 hydrogens here, 2 hydrogens here balanced. Oxygen, we got 2 oxygens here, and we got 1 here, and you see 2 times 1/2 is 1, so 1 plus 1 is 1, so it is balanced. But we cannot leave balanced equation as fraction at the end of process, so we have to multiply everything by 2, the whole reaction, all those coefficients by 2, and that is your final balanced oxidation reaction. Okay, sometimes we have to trial and error, but you have to start with this number here, from the this number, the balance. So once you balance the electrons, then that coefficient will help you to balance the other elements. Again, first for half reaction, first we have to balance the atom, and then we have to balance the charge. But for the complete reaction, you will have to find you have to balance the number of gained and lost electrons, and you can use those coefficients to the common number. Well, here, yes, I mean, because in 2, that will be 2 in oxygen. So you got the point here. Okay, so feel free to ask me questions if you have any about the redox reactions here. We'll see you next time.